Hello, hello student. This is Engineer Selassie from Hello Academy and Brain Boosters. Today came with another chapter, and today we are going to discuss about the process APIs. And as usual, we are going to use the book Operating Systems 3 Easy Pieces by Andrea and Remzi. So let's get into it. I'm going to demonstrate each step. So the process creation and control in Linux system, we have the system calls like fork and exec, and the third routine is wait. Can be used by the process issue to wait for a process it has created to complete. Basically, I will demonstrate this fork and exec system calls. And what about wait? Because wait will be used for when we use fork, the parent process will wait until the child process is completed. If we don't use wait, the parent process will terminated before the child process, and the child process will be become zombie state. So we shall see it in a minute. So as you can see, the fork system call, this system call, what it does is it creates a new process from a running process. The newly created process has its own copy of address space, register, and program counter. This code show us how to use the fork system. This is from the book. As I told you, you can go to online and you can download it. So we can include video H, stdlib, and stdh, and we have here the main argument, as you can see, argc and argv, and we are going to print hello world, and we have also get PID, and this is the fork system call. So this is the child new process, and the parent goes down this path, and it will say I am the parent of PID. So it will get the PID, and this is also the output. As you can see, hello world, PID 9146. Hello, I am the parent of 29147. As you can see, 29147. So the most important thing at this stage is that the program which is created is just exact copy of the parent, okay? But the issue is the PID will be different. For example, the parent is PID 29146, but the child will be 29147. So it replicates the exact copy of the program. We will demonstrate this one. I'll show you, I'll create a program and we will see this, okay? But the most important thing is the fork system will replicate itself, and it will duplicate the same program in different PID address. So just to demonstrate this, what I'm going to do, we are going to use the same code. You can go and check, you can download, but let me show you this this process. Let's go to the Linux operating system. This is Linux operating system, so let's log in. Let's log in. So I am in the API, okay? We can go and download it, and if you see the process, I have PC1, PC2, PC3, PC4, and I have just make a little bit change to make it executable. I use else, and what I'm going to do now, okay, let's execute. GCC is the system in Linux. So what I'm going to do, p1 dot health and p1 dot c. Let's run this. Okay, let's execute this. And now what we are going to do, let's execute p1 dot health. Okay, so as you can see, hello world, this is the PID of the parent process 71695, and the second line of code, I am the parent of 71696, as you can see, because hello, I am the child. Okay, this is PID 71696. This means the fork system call will help us to create the exact replica of the parent process, but it will have different PID. Okay, this is a demonstration of the Unix, and if you can see here, the original P1 process printed PID, this as per this code 82773. This is a parent process. Then a child and a call to fork is made with which creates a new process with PID 82773. A child process with a PID 82774, exactly, not 3, 82774. That is almost similar to the parent process, the child process. So the new process, as you can see, I am, yes, the parent is the same, 82773, but the child will be 82774. Notice that the child process begin executing after the call to fork instead of at the start of the main. And this is very important. The child process has its own private address space, register, and program counter, which is different from the parent process. Fork return 0 to the child process and child PID to the parent process. The order of execution of the parent and child process is non-deterministic depending on the scheduler. So this is what happens is, for example, the parent process was created and then the child process was created. At this point, what happens is the parent process will be terminated before the child process terminated. And if you check the status of the child process which is created now, it will be in the zombie state. That means because the parent is already terminated. But the next what we are going to see is the wait. Okay, this is another system call. This is the wait system call. Allows the parent process to wait for the child process to finish first before continuing and terminating. This system call will not return until the child has run and executed. As you can see, when we include wait, then it will wait the child process to be executed before the parent process is executed. So parent gets down this path now. So this is the code also P2C, and if you see as per the book, as you can see now the child become, this is the second one, I am a child process. It will come in the second output. After the child process is completed, then the parent process will be terminated. So in this way, the program will become deterministic. Okay, the result is deterministic. So Adding the call to wait on the call block for the parent process guarantees that the child process will finish first before the parent process finish. This deterministic order of execution. Just to show you in the Linux operating system, again, what we are going to do, let's clear this one. We are going to use ls command, ls. As you can see, we have p2.c, p2.alph file. Now I just downloaded it. You can go and download it. So let's compile it. gcc p2.alph, again p2.c, p2.c. So after this, let's compile now. So if we compile this, as you can see now, hello world, this is the PID of the parent process 76304. The second one is hello, I am a child. As you can see now, the child comes in first and it executes. After its execution, the parent process, I am the parent of 76305. This is PID 76304. So will be created. So in this way, we can differentiate between the four. The other very interesting code is the exec system call. Okay, exec system call. This one is a little bit different. What it does is it will replace the calling program with the new program. Okay, this is run a program that is different from the calling program. Then I will demonstrate. I will write a simple C code and we will compile it and we will see what does it mean. But just for your information, the fork is just duplicate the same program, but the PID is different. But in the exec system call, what we are going to do is that the program directly, the whole program will be replaced and the PID will not be changed. Okay, the child process will have different code: static data, address space, register, and the program counter. And in the previous example, code and static data of the child are the same as the parent process after a call to the fork. But in this situation, what it does is once we invoke or once we put the exec system call, what it does will be it will replace. Okay, it will replace the whole. So here, as you can see, we have the main argc, we have argument v, print hello world PID, we have the PID get PID, and we have the fork. Okay, fork. If the fork failed, as you can see, else and print and character, and so this one is the program word count, argument file, count, mark of array. So let's go and see this. If we run this program, it's better to see it in example in Linux. So what we are going to do, let's go to our Linux system and let's open PC3. So what we are going to do, you can see ls, we have PC3 here, and I just modify the core PC. Okay, so what we are going to do now, let's do gcc This is the common for Linux system, okay? Always this is a compiler. So elf and PC. Okay. So now we already run, and now let's compile it. P3. Okay, so as you can see, hello world. PID is the program identification number is 79769. Now if you see hello, I am a child, and PID 79770. And as you can see, a new program is already executed, 32.123.966PC3, and hello, I am the parent of 79770. I am the parent of 79770, and PID 79769. Okay, 79769. That means the whole program is changed here with the parent. The output of the parent, as you can see in the PID is completely replaced by a new program. So what does it mean? So the fork system call is used to create a separate duplicate process. The PID will be different, okay? But exec, when an exec system call is invoked, the program specified in the parameter exec will replace the entire process, including all threads. The PID will be the same, but the content is different. It will replace the entire process, so don't forget this point. And I will show you in a minute what I am talking about. Okay, I wrote some command, so we shall see it. Why to separate fork and exec? Just before we come to here, what I want to show you is, let me demonstrate this the fork and exec system. I wrote two codes. So what we are going to do, let's go to our Linux, and let's close this one. Okay, I created two folders. One is fork, the other is exec. Okay, exec. And in the fork, open the two folders in the desktop, fork and exec, and place. This is step one. Okay, sample C programs. So what I did was, the first one, hello, this is fork. Okay, so what I have is hello.1c. This is a very simple program, as you can see. Let me open the code. The code is simple, just as you can see, stdioh, this type.h, uni stdh, and this simple C code, what it does is just the first thing what it does is let me remove this before the fork, and I will show you after the fork. Okay, so what we are going to do, let's save this file. Okay, let's save this file like this. It simply says hello academy and plane boosters, and it will get the PID of this program. Very simple program. And let me delete this file as well. And what we are going to do, let me open the terminal here, and let me see how many files we have. As you can see, we have hello 1, you see, hello 1.c, and we have hello 1.elf files. And what I want to see, let me compile now. GCC or hello1 dot hash hello1 dot c. Now let's compile it. hello1 dot hash. So as you can see, it does only simple, just hello academy in plain boosters, and the PID is 84203. This is the first step. Okay, now what we're going to do, the second step, what I'm going to do, I'm going to add the fork system call, and we shall see what's going to happen. So let's open the file. Okay, let's open the file. This time I'm going to add a fork system call here. Okay, as you can see, fork the fork system call, and let's save this file, and let's close this and save. So now we add the fork system, and let's go to our ls. As you can see, hello.c and hello.elf files are the same. I didn't change nothing. Now let's run gcc or hello1.elf hello.c. Then let's compile it. hello1.elf. Okay, so as you can see now, it duplicates 2 times. Okay, now we have 85720 and we have 85719. The PID is different. Okay, the PID is different, but the code is the same. The code is the same. So this is a demonstration of the fork system. So this is what I want to show you. The second one, let's close this. The second one, what we are going to do, we have the fork system. Okay, this one is completed. Now let's go to the third. Now in exec system call demonstration, what we are going to do, this is exec. Now we have 2 files. Okay, hello1 and hello2. Okay, hello1 and hello2. In this system, what I'm going to show you is that, let me open the files. This is a simple C code, and as you can see, this is the main. We have an argument C and argument V, and what it does is it simply prints the PID of hello1.c, and it will get the PID. Again, just we add hello academy and null. Now we add here execv. You see, this is another clone. We have a lot of variant of exec command system call, and in this system call, what we use is execv, and what it does is it will go to the second hello2. This is my second code, and it will get, you see, I am in hello2. Okay, it will get the result of this, and the print f back to hello1.c. So the exec as we have discussed, it will completely change the program. So we will see when we compile hello1.c, then we will see that this program, what it does. Okay, let's go to this folder and let's open the terminal in this folder. So let's see. So we have hello1 and hello2. So when we use this exec, it will change. So what we are going to do, let's compile gcc hello let's see. So okay, no problem. Everyone. Now this will give us an output in the folder. Okay, because I have already, this one is completely changed. It's completely changed. It's completely changed. If you want to see, no problem. What I want to do, I can delete this, I can delete this. Then I'm going to show you. Look, let me run the code again. hello1.c and hello, because if I don't give the name of hello1, when I run the second time, it will replace it with for hello2. So if we give the name, it will not replace. So as you can see, automatically hello1 is created. In the same way, let me hello2.c and or hello2. Now if I run this code, it will not replace the output of the hello1, but it will give me another output in hello2. So as you can see, I have hello2 here. So what I'm going to now, I'm going to run hello1. Okay, when I run this, as you can see, what we get here, the PID of the hello1 90641 is already there, but the program goes to the second and it will replace it. You see, I am in hello2.c. I am in hello2.c, and the PID of hello2.c will be 9064. That means the PID of the hello1 is completely the same. There is no difference. Okay, in the same PID, but the program is already replaced by hello2. That is the beauty, because here execv is already included, so it goes to the second program and it gets, I am in hello2, so I am in hello2 is printed, and printf back to hello1 will not go back because there is nothing we give it in this situation. So in the simple term, this is the demonstration, simple demonstration. I wrote simple codes, and I hope it might help you. It might help you. So let me go back. Here. Okay. So now you understand the idea behind fork and exec and wait system calls. These are very important. Now the last idea which we have to discuss in this video, why to separate fork and exec. This is also demonstrated in the book. So why to separate fork and exec. Example, the output of wc, instead of being shown in the screen, is saved, redirected to a text file. As you can see the prompt, I will show you in a minute. wc p3c and new file text. To implement this, the shell closes the std out of the process after fork, then opens new file.txt file before calling exec system call. This works because the open system call starts from zero when looking for available file descriptors to use. Since std out, this is for the file descriptor 1, was closed, the call to open system call will assign file descriptor 1 to new file.txt and will treat it as the standard output after call to exec system call. So the piping we will come, but let me show you this because it's better to use Linux again. So this one is already completed. Let me close this file. Now let me go to the download and this file, and let me open the terminal. Open the terminal. We are here now. So in the API folder, what I want to show you is that if I just, you can follow me, just write word count pc3.c. So if I run, as you can see, we will get only this one. Then let me p3.c new file.txt new file txt. Now nothing happens. Let's say ls new file.txt. okay, as you can see now. And let's use cut new file.txt. the same, as you can see, wc word count pc3, and again when we after we use this new file, the new file, the output is the same, 32.123.966 pc3 and 32.123.966 pc3. So this is a simple demonstration of how the redirection works. So this is implementing a std out redirection to a file in Linux demonstration. This is also from the book. The code, we have the code we have seen now. Okay, how the two are the same, but let's go, and we have seen it, but let me repeat it again. So we have seen it already, but let me, okay, list, as you can see, we have P4C. If you want to see P4C, just P4.c. So the code is Z. Here is the code. Okay, the same code. Okay. What we are going to see, GCC P4 F. We have 4. Sorry. Dot p4.c. Also, instead of O, I use this C. 4.c. Okay, now let's compile it. p4 dot. Okay, now when it does nothing, but when we see now, we have the output file here. p4 dot output was seen. So that is the demonstration, simple demonstration. And the other thing, implementing std output in addition to the file is demonstration. We have demonstrated already. There are so many processes like related system calls, kill. For example, I have demonstrated this, how to send the signal to the running process, to stop it, to kill it, to resume it. All this is done by kill signal, used to send signal to a process. Most of the time we can use Ctrl+C, and to stop it Ctrl+Z and the like. And signals subsystem enable the delivery of event to the process. Process and process groups can have signal handlers via signal system to perform a specific action whenever a specific signal is received. Processes are associated to users in order to provide ownership and control, as well as limited security and protection, and get user ID system call to return the user ID of the user of the process calling it. If you want to see the man page is very important to check the APIs. So if you go to the man page, signal, and you can see, you can read what is signal, and see signal handler, and include signal.h description. The behavior of signal varies across Unix version and has also varied historically across different versions of Linux. Avoid its use and instead signal set the disposition of the signal, and so on. As you can see, you can go ahead and read. It has huge. The other is we have seen this already. So almost this is what the fork and the exec. So in general, this is the most important things which are included in chapter 5, and I hope it gives you some idea of the chapter. The other issue what I want to discuss is the other why to separate fork and exec. Essential for building a shell and interface program that accept command from the user to access the service of the operating system. So example, bash means born again shell, and Z shell in Linux. These are for Linux. Command prompt and PowerShell in the window. With this separation, the shell can run some code after the call to fork, but before the call to exec. It allows the shell to alter the environment of the above to be run a program by exec, enabling more features, example pipes and input-output redirection. So again, when we go to our Linux system, And what we're going to do, if I want to see what shell I'm using, you can use this echo shell. You can use this shell. So as you can see, bin bash. So just use which bash. So as you can see, user bin bash. Then what we are going to do, file user bin bash. So as you can see, it's executable. It's also a program, okay? elf lsp pi executable. So the version 1 dynamic, and this way you can get information about your system. So all the codes are readily available online. I recommend you download it and practice it like this. The most important thing is the fork, the weight, okay, the weight, and the exec system calls, and the file redirection code. And we have seen how to redirect the file. This is P4C, and we have seen already my simple code, and we have seen that how the fork and the exec system work. So guys, this is chapter 5, and the next video we will discuss about chapter 6. And till then, thank you so much. This is Engineer Selassie from Hero Academy and Brain Boosters.